We will start our discussion of functions with a very basic introduction. We'll look at definition and then certain basic manipulations that you can do with functions. So let's begin with how I would recommend thinking about them. Essentially, functions are abstract mathematical objects that send an input to a unique output. And the unique part here is very important. In fact, this is what distinguishes functions from sort of general input-output operators. You need to have only one output in order to be a function. You can think of them as numerical, but they don't have to be. They can be operations that are more general than just dealing with numbers. But on the CLEP, you may see at most one example of something like this. So the notation for this is somehow very standard. We say that you have an input value x, and the output value according to the function is f of x. So I'll say that we will input something like x, and we'll output f of x, where f defines a kind of rule for what to do with x. So for the CLEP, we'll look at various ways of quantifying what kinds of inputs are possible, what kinds of outputs are possible for a function, and we'll discuss how to plot them in nice ways by looking at standard examples you might see and learning sort of the basic principles that govern how to plot functions in the Cartesian plane. So first, let's look at a few basic exercises related to this definition of functions. So just to give you an indication that a function doesn't have to be just somehow an algebraic relationship on the inputs, we can look at the following. So we will define f of x to be 1 if x is a whole number. We will discuss these also in the next section and in module 4 as integers, and we'll say it is 0 if otherwise, if x is not a whole number. So we can look at how f works on certain examples. So f of 0, is that a whole number? The answer is yes. So according to my rule, I output the value 1. So I would say f of 0 is 1. Similarly, f of 3 is determined by asking the question, is 3 a whole number? The answer is yes, so my rule says to output 1. Conversely, if I say f of 1/2, I have to ask the question, is 1/2 a whole number? The answer is no, so I output 0. And similarly, f of pi requires me to ask the question, is pi a whole number? It is not, it is an infinite decimal, so I output 0 as well. So I'll just remark that f is not defined algebraically. It is somehow maybe more complicated than other functions you've seen where all you had to do was multiply x by some things, maybe add some things, do some divisions, working with the kind of basic operations of addition, subtraction, multiplication, division, exponentiation. This is somehow outside of that world, but it still fits the definition of a function. So it's good to think about things at this abstract level as you get ready for the CLEP exam. So another nice thing we can practice is simply evaluating a function. So if I say that f of x is given algebraically as 3x cubed minus 1, then I can sort of look at what different inputs go to under the output rule f of x. So if I say input x equals 1, then under my rule, the output is f of x equals 3 times 1 cubed minus 1, which I can simplify to 3 minus 1, so 2. So these are my inputs, and these will be my outputs. So I can try x equals 0. This goes to f of x equals 3 squared minus 1, so minus 1. And let's just do one more for good measure. Let's try f of 2 So this goes to 3 times 2 cubed minus 1. So we have to remember that 2 cubed is 8. So 3 times 8 minus 1, 24 minus 1, so 23. So in this sense, I think it's very easy to interpret a function as an input-output rule. There's an explicit algebraic relationship on how the output depends on the input x. All I had to do is cube my inputs, multiply them by 3 and subtract 1, and that was my output exactly. This is somehow, I think, the standard definition, or rather not the definition, the standard way of seeing functions on the CLEP, that you're likely to see them defined algebraically on the inputs. Let's look at another example that tests more symbolic understanding of functions. So suppose I define f of x by the rule x plus 2. You can also think of this if I was to visualize it, which we will practice in coming submodules. This is the plot of a line. So the rule is a linear rule. I take the input, and my output is just that input plus 2. So we can check f of 0 is 2, f of 1 is 3, f of 2 is 4, and so on. So here's an interesting exercise. Let's run this function twice. So we'll essentially apply the rule 2 times to the initial value 1. That is, we'll compute f of 1. How do we do this? Well, first I evaluate f of 1. So this is 1 plus 2 by noting that f of 1 equals 1 plus 2. So I apply the rule once, and now I have to evaluate f of 3. So this is 3 plus 2, so 5. Okay, so you can think of this as iterating a function. I don't want to just apply it once, I want to apply it twice. In general, we could apply it any finite number of times. And in some cases in mathematics, you can even apply a function infinitely many times, and it will give you a unique output, which I think is a very beautiful subject and worth looking into, but it is not covered on the CLEP, so we will not be discussing it in further detail. So just one more example that you may see. I can define a function in what's called a piecewise way as follows, for example. I can say the rule should be output x plus 3 if x is greater than or equal to 1, and output 2x minus 1 if x is less than 1. So this is sort of strange looking. It's not just one algebraic relation. It's two of them, and which one I use depends on what my input looks like. If x is greater than or equal to 1, I use the rule x plus 3. If it's less than 1, I use the rule 2x minus 1. So we can plot a few values here. F of 0 would then be 2 times 0 minus 1, so minus 1. And this is because 0 is less than 1. So I use the second rule. On the other hand, f of 2 would be 2 plus 3 equals 5 because I used the first rule. Okay. Using this type of brace here and having multiple conditions is called defining a piecewise function. And I think it's somehow helpful, if you can, to at least plot what this looks like. So we'll draw a little Cartesian plane here. You know, we're doing things very roughly. So for the rule x plus 3, this is that rule. And then for the x less than 1, I think the picture would be like this, where there's somehow a jump in between these two values. So we essentially have two different pieces of a line put together, but then there's a gap between there's a jump at essentially x equals 1 because I changed the rule there. So the way that the function operates changes at that point. So this is again called piecewise because I have two different pieces here. This is the first piece, this is the second piece, and it's interesting from a mathematical standpoint to note this gap here. Calculus gives us a language to describe how significant this gap is in terms of, do I have to lift my pencil to be able to draw these two lines? Is it a substantial problem for applications to have this gap? There is a very beautiful language for discussing these things, but this is covered in calculus, so it's not going to be covered in this exam, but something to look forward to if you're interested in these type of mathematical phenomenon.